Okay, welcome to class. It's Thursday, March 31st. Unfortunately, I can't be there with you today, but I have prepared this short screencast lecture for you to introduce you to the topic for the day. You've also hopefully completed the pre-activity, which helped you get some background information that will be useful as you do today's task, which is a case study. So first, some announcements just to keep us all on track. Exam number 2 is 1 week from today, so next Thursday. This will be an in-class exam, very similar format to exam number 1, and I also have posted, or will post very soon, a review guide that is current through today's class to help you as you study. So today, hopefully you have come in with this pre-activity, which you should turn in before you leave. Make sure that I get those in a pile. And then the other thing today is this case study, which you'll start today in groups, and then there's a take-home portion that you'll complete after class, or if you get to it, you can complete it in class, and that is due in class at the beginning next time we meet, so Tuesday, April 5th. So you've done some background work on environmental health and toxicology. Today we'll extrapolate some of that information into a case study on PCBs, polychlorinated biphenyls, a persistent organic pollutant. So just a few quick things to help set you up for this task. One important thing about toxins and chemicals, and a factor that influences how they move, is solubility. So this is what the compound can dissolve in. So we've got chemicals that are water soluble, meaning they can dissolve in water or be suspended in water, meaning that they can move rapidly through the environment. So wherever water goes, these water-soluble compounds can also go. And water is pretty much everywhere. Other molecules are not as soluble, so but they are soluble in oil or fat. So these things generally need some kind of carrier to move through the environment. This could be oil itself, or it could be the fat of an organism, so that wherever that organism goes, or wherever the organism that eats that first organism goes, so does the chemical. So you want to keep solubility in mind as you think about how PCBs move through the environment. So polychlorinated biphenyls, or PCBs, are highly stable molecules. They're not water soluble to a large extent. They're minimally soluble in water, but they're highly soluble in fat. We've got multiple different types of PCBs, which I'll talk about later. So these are molecules with 2 phenyl groups and then various numbers of chlorine atoms as well. So they have more than one polychlorinated, but some variable number. So a little background on PCBs, and this is not the only place where it's a problem, but where I did my graduate work in Bloomington, Indiana. Westinghouse Electric was a prominent corporation there, and they used PCBs, as was common to use PCBs, in electrical equipment and other parts that needed to tolerate high heat. So PCBs are great insulators, so they're great for electrical capacitors. And when these capacitors would go out of service, they would be dumped in landfills, or maybe just left sitting out around warehouses or things, just sort of disposed of casually in the environment. So one such landfill was Neal's landfill, and it's out here in Bloomington, which accepted these municipal wastes. Well, there are also springs that run around these landfills, which became and still are contaminated with PCBs. So one thing about these sort of pollutants is that they're also difficult to remove from the environment. So over time, they get dispersed over large areas as they continue to move through systems, but they never just break down into not harmful components. So the case study today regards how PCBs came to be found in remote Alaskan lakes. And the first 4 parts will be about this question. The last part of the packet, part 5, is the take-home activity. So you just bring the whole packet in next week on Tuesday. So I should have mentioned that PCBs are endocrine disruptors. So in the 3 classes of toxins I asked you to look at, PCBs are endocrine disruptors, meaning that they can be toxic and harmful even in very low doses. The slides told you about how the effective dose, the ED50, doesn't show the same pattern for endocrine disruptors as for other toxins. So PCBs can be a real problem in the environment even at really low doses. So just a few helpful notes as you move through this case study. You'll be asked to make several hypotheses, and I just want to remind you that a hypothesis is an objective explanation for an observed pattern. And a good hypothesis needs to be falsifiable, meaning we need to be able to test it in some way to prove it false. A lot of hypotheses follow an if-then sort of format. So for instance, if DDT is the cause of low eagle population sizes, then we would expect individuals exposed to more DDT to have fewer offspring. Okay, so if one thing, then something else. When you get to later on in the case study, it will ask you to interpret some figures. And these figures show you data from multiple PCB congeners. A congener is a general term for something of the same type as another thing. So this is just referring to that there are many types of PCBs. They're all the same class of chemical, but they have different numbers of chlorine atoms attached to them. So they're all PCBs, they're just specific types, distinguished by their particular molecular structure. So you can think of, when you hear or when you read PCB congener, you can just think of that as a type of PCB, all under the same umbrella. So a few slides on how pollutants move across the globe. Some things can be airborne and move through the atmosphere in the air, either attached to dust or in dust clouds or attached to water molecules. So this is showing you some patterns of wind moving things across the globe. So these outlines are where the air pollution goes, about the average direction and force of that wind. So you can see that different places have different patterns for moving things across the globe. And then the colored in parts are showing you places that experience signs of pollution in the atmosphere. So the bottom line here, the wind can carry pollutants across the globe. Another force that carries materials as well as energy by heat across the globe is the ocean conveyor belt. And I believe we've talked about this. So this is that there are cold currents that are deep in the ocean that are moving, and in response to wind and in response to solar energy at different parts of the globe, they warm up and they rise, and that warm water moves other places. And then at some point those warm waters sink and become cold again. And so this idea of a conveyor belt is the movement of warmth as well as materials across the globe through the oceans. Another way that materials move around the globe is in the bodies of animals. So we know that various birds migrate. This is showing you bird migration across Europe and Asia and Africa. So a lot of birds move very long distances over the span of a year. Whales, turtles, sharks also move through the ocean. Here's another picture of humpback whales moving from their winter breeding areas in 2 different locations to where they feed in the summer. three winter locations. Okay. Another migrating species are salmon. So these breed in streams and then breed in streams and come out into the ocean, migrate around, come back into other streams. So these are all ways that materials move across the globe and things you might want to think about as you complete this case study on movement of PCBs to Alaskan lakes. For the final section, section 5, which is the take-home, here are some resources. These slides are also posted on Moodle. Okay, so that's where we are. Complete case study parts 1 through 4 in your groups. It'll be more fun, I think, if you work in groups. And then finish that up, finish part 5 at home, bring it in with you to class on Tuesday.